Oh, are you muted?
I am muted.
No, yeah.
I should be. Yeah. All right. Thanks.
Jan, where's the chat?
Up here. Well, good. So let's start then. So we're going back to reversing lists.
Thank you for this very nice introduction. Okay, so I want you to look hard at this this program to see what it does. And so so it has some linked list P0. You take a reference to P0, reference to null, and then while the reference that was initially to P0 is not null, you do this swapping thing. So it's the code for in-place list reversal. So you allocate only 2 cells, 2 references, and that allows you to reverse to use the existing cells to have to construct the reverse list. Of course, you are losing the initial structure of the list because you're using the same cells. So it in fact changes every time. So it every time of the body of the loop is to take the cell that is stored at R, move it up 1 step of like it takes the p.tl, and then the p.tl is replaced with the value of s, the value pointed by s, and then s stores this new cell. So if you imagine something like this, nope, never mind, I don't have a picture. I mean, actually, we don't really need a picture. We could just try to see what we need to prove this. But the idea is that you have a bunch of cells like this, pointing all like that, and every time you get to a cell, you're putting the pointer to the next cell to the previous cell, and you're moving like this all of the pointers back to the beginning. So if we want to prove this, we can the first step is to specify the states before the loop, to specify the state that we want after the loop, and then try to find a loop invariant that combines the two in a more general way. So before the loop, we have so I can do something like this. That's fine. You have some. All right. True. SPLV, I think. You have a P0, yeah.
So R and S are quite different, right? S is kind of inherently a reference, but R is just like a local variable that you're mutating, right? You could have removed it to be a let and a recursive function instead.
Yeah, you could do that and use the stack instead of a heap to do that.
No, you would still use the heap on S, but you would just keep the R in the recursive position.
You need some heap. Yeah, I guess you can use the stack here.
You see what I mean?
Use like
too much state here at the point.
But the whole point of this is that you're modifying the heap. So
you would still modify the heap. Okay, that's not offline.
Yeah, but I mean, so, if you're worried about state, you should probably not write this function.
Why? No, I mean, no, I disagree with this, but we can take it offline.
You mean like
you can write functional programs?
The language is imp.
No, it's
not. No, it's not anymore. But the point. So if you're having a purely functional language, separation logic might not help you out much. Might make things more complicated. But if you have some state, then you want. I mean, we're working on something on the camel now, and so you have a bunch of things that manipulate the heap, but sometimes you don't, and so we have a special mode for when you don't. But this, I mean, if you want to reason about the heap at some point, so you do need separation logic. Yeah, okay. All right. So at first you have R that points to P0, S that points to null, and you have the thing that is interesting, the list. So P0, and we write something like this that points to some list. So we write M list L. So what do we want after the loop? So to be able to prove this function correct. So we're returning S, the bank of S, so the content of the cell S. One. Do we know that what R points to? No, very good. Do we know what S points to?
M least reverse L.
Huh? N points to not a cell, not an like some reverse cell, yeah. But so we don't know where this will. We don't know the actual address. It is not specified here. So it will be something like there exists some R, some Q, so that S points to Q, and then what is interesting and what it will be returned is Q, and so Q squiggly points to M list of rev over R. And so now we need to find an invariant that combines those two things. So there will be two pieces of lists. So there will be something like there's L1, L2, some P, some Q, such that R points to P, S points to Q, and then P and Q points to lists, and they are related. So like something like this. Nope, squiggly arrow. M list of L1, L2, and then some relation between L1, L2, and L. So because I'm not trusting myself to do that correctly. So this is the correction. So before the loop we have this. After the loop we have the following. We don't know the value Q. And the loop invariant will look like this. And the relation was between L1 and L2 and L was this thing. And the relation was between all of those lists is a pure fact. It's just in your logic. So then you need to reason about all of those things. But that's pure reasoning. The separation logic part is this one. So that's the actual proof if we want to do it on paper, but it's a bit maybe I mean, it doesn't help much to read it. So we should do it. So I can show how it's going if you are in Iris, for example. So I will be here. Yeah, that's good. So that's can I do this? Yeah. All right. Can you see? Yeah, thanks. So it's using heaplang. This is the toy language that is developed to demonstrate Iris capabilities. So it's a functional language that is also concurrent. This I'm not explaining, but I will show you just the definition of reverse. So it looks like this. So you have a bunch of notations. That's all of those column things are every time a custom notation for the language everything. So it's a very deep embedding of everything that is there. There is no while loop, so it's just a recursive function. But I did keep the references. So that's the same as the program. And so when you want to prove this, you write it as the following. So this is a triple. The fact that there are 3 curly braces is called a Texan triple because they do everything bigger. So you have M list L P0 as precondition, and then it returns some value R such that M list of list.rel of L R. So R points to this list. So I'm showing you so that you see better what's happening, but I won't be able to explain everything now. So we are working with a WP, which is usually the case in most many formalization when you do proofs on a computer, you like to have a weakest precondition rather than Hoare triple, because you need to, it's easier to be more general when you state dilemmas. In fact, the notation here is a notation for a WP. So you have your program here, you have your Kirk hypothesis here, you have your Iris hypothesis here. This is an implication that we haven't seen, but it's like the magic wand that you might have heard of. And those two things are, in a sense, separated by a star. And so that's the conclusion that we have. And it goes like this: we unfold, we applied a bunch of tactic that handles every construct of the language. So pures is anything that it does not involve a state, just try to do it. There is an allocation here. So we allocate, we give it a name. So this is the relation. So this R is the R of the logic. And this R is the name inside of the programming language. So that was, that's a pain point when you do it on paper and you're like, am I doing things like that make sense? But whenever you formalize it, it has to be clear. This is clear. This is you could call it anything, anything, and you will have this that will replace the R. So R takes the value of this location. So I have to show you. So this R is now a location. So it's inside your logic. You're able to reason about it like in Calc normally. And then you have an Iris hypothesis that says R points to P0. P0 being the ref, the content of the ref. So now we do this step. You know that you see that the ref of P0 became some value. So this symbol is for the value of something. So you can have a location, integers, anything. So this is a location, so it casts it into values. And so it's a substitution-based semantics. So it just replaced the piece of expression ref P0 with this new value. You can be substitution-based in Iris, that's simpler, but you don't need to be. Like for bigger languages, it would be maybe less practical to have a substitution-based semantics. So so this is pure. You're replacing this R with this R. So like the italic R is this one. And then you have R that points to P0 in your hypothesis. And then R is replaced with R. You have a second allocation, a bunch of pure steps that you can just do with a mess. Maybe not, because there is. And then you have your while loop that you just remember to have something more easier to manipulate. And then you do a bind rule. So it's like the consequence rule, but the result might be important. The sequence rule, but the result might be important. Then you have an invariance, so it's the same as the one we had on the slides. And so you need to initialize it. So when you initialize the invariant, you have to say with which hypothesis I need to, which ones I need to use. Oh, I didn't talk about hpost. It's like the continuation for proving the post condition. We'll see that later. So we need to establish the invariant. So what do we need for the invariant? We need we need the list. We need the reference R, the reference S. And so we say we'll take those hypotheses and we made a new hypothesis that is called HINV. And so now we have to prove INV with this hypothesis. So we say there exists some value. We don't say which one it is. There exists some L1 that is the empty list, some L2 that is the list entirely. And so we have to prove this goal. So all of those evals, we call them, like a question mark goal is an eval saying we don't know what it is, but we'll find out, and then we'll backtrack to make sure everything's okay. This is the frame rule. It's using, please try to solve the goal using this HR. So frame rule, we'll see just very soon what it is. So there is R points to P0, and it probably corresponds to this R points to question mark. So will you please try to instantiate it so it disappears. So it disappeared both from the goal, from the hypothesis. The same with this one, S points to something. It was in fact now because that's the hypothesis we have. Then we have M list of LP0, M list of LP0, iframe. And then the fact that null points to the empty list is the same as null is equal to null. And the fact that L is, I mean, and this fact is also simple reasoning, like correct reasoning. Okay. Yeah, this is the log rule. We'll see it later, which just magically does induction on nothing. And then we need to distract the invariant and do a bunch of reasoning. So we have an if. So we do two cases. If the P is pure, is null, it simplifies to this. So we basically need to establish the invariant back. And if the P is not null, we step through. And after stepping through all of the assignments inside the body of the loop, we need to reconstruct the invariant of the body after the body of the while. And so again, we do I asset of the invariant with the hypothesis we want. And we say, oh, okay, never mind, the L1 is not L1 anymore, it's X const L1, and the L2 that was X const L2 is not X const L2 anymore, it's just S L2. Framing, some reasoning on lists, and then we are done. Okay, so it's hard to read also here, but it's basically the same as the slide. It's hard to read on the slide as well. True. Here. All right. Say now that you want to prove this program. So try to know what. Okay, so it's a length. It's a program computing the length of a mutable list. So it takes some pointers to P. P is the pointer to the list. Some pointer to 0, some reference to 0. And then while the F does not point to null, increment the reference to the integer and take the next step in with the pointer to the list. So just iterate on the list. So I chose a while loop to make it more complicated. If we do a recursive function, it's easier, but it's still hopefully helps to show why we need some other things. So the step before the loop is, so we have some P that points to L, some F that points to P, and some T that points to 0. So at the end, what do we want? So we want T that points to something, because we return bank T, the value of the cell T. We're just checking that you're following now. Yeah, length of the list, perfect. What else do we want? I mean, that could be enough. If we just want the length of the list, we're good. But maybe we want something else. Yeah. F points to null might be useful, although we were kind of throwing it away. It's a local reference, so maybe it's not that important. What else could be interesting?
P to still point to the old list.
Yes. Yeah, we still want to keep the list, because if we have the length and then we don't have the list anymore, yeah. So we still want that. So if you try to write a picture of this, you have something that looks like this. So after a few steps, you have P pointing to some prefix of the list that you don't want to lose, and then F that points to some value Q that points to the start of the rest of the list, L2, and T that points to some integer. And so the question is, how do we do this? How do we have like split the list into two pieces? So the idea is that we want to be able to describe not an entire list, but just a segment of list. So we'll have to invent something that looks like this. P points to L1, but it does not end on null, it ends on Q. And the Q is not like, it does not belong to the domain of L1. It's just a value inside it. However, Q points to the start of L2, and this is a regular predicate on representation predicate on lists. So the invariant would look like this, and then we're able to complete the proof. I think there is even something here. Yeah, there's that. Wait, no, never mind. That's the recursive version. Not interesting. So exercise, but I basically said it already. So if you have this is the reminder, this is the predicate for list, and the exercise now is how do you define the same predicate for the segments? You have one thing to change. In the null case, in the nil case, yes, you change P to Q. Perfect. Very good. So yeah. So you have some reasoning on list segments. So when you have a cons, you can split the list into two, like this. But if you have a concatenation of two lists, you can also split in the middle. You don't need to cut it at the beginning. And then this is not helpful for lists only, but you can specify a bunch of other things this way. So this is an example with a mutable queue where you can add things at the end as well. Wait, no. Can you add at the end? Yeah, you can add at the end. That's the point. And then
can I ask?
Sure.
How you know where to split if you have a L1 append L2?
So this exists. You don't know it. It depends on your heap. So the proof of this goes like, oh yeah, there exists this one, there exists this one. Oh yeah, and then we're here. So it would be by induction on L1, and then so it's the same as this one. Like you don't know what is it. It depends on the heap. Yeah. Blah 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 blah. Okay, so we have the same for trees. I'm guessing it's I mean not surprising. So that's the second example typically when you do suppression logic. So if you have so this is a record in a camel with 3 mutable fields. One item that stores the value at your node, left and right that are pointers to the same type. The corresponding logic in your theory would be, so this is a Coq syntax. You have an inductive with leaf with no values and node with some value. So it would be something like this. I think it's clear. So you have, this is the representation of the heap, a bunch of boxes with a bunch of pointers. This is the representation on like in your theory. So just an abstract syntax tree, just a tree. And the goal is to define a representation predicate for trees, and it's again exercise, but it's the same as for lists. So basically, you match on on T your logical tree, and when it's a leaf, you say P is no, and when it's a node, you say there exist 2 pointers, one for the left, one for the right, and you recursively call your representation predicate. Yeah. Yeah, I don't know. So I'm going quickly. I'm assuming it's fine, but please interrupt. It's hard for me to know if it's not fine.
So trees are unlike lists, the opportunity for you to share subtrees.
Yeah.
And then what happens? Because yeah, your M tree is rules that out, right?
Oh yeah. That is a good point. So those stars means that there is no sharing in the trees. So that means you can run a bunch of algorithms that assume no sharing. If you want to use a bunch of sharing, then it would be weird to have mutable trees. Maybe it depends. It depends what you want. If you have a bunch of sharing, of course, it's more complicated. You need some different things. We'll see some structure with sharing that makes a bit more sense, maybe. Okay, so now imagine that you want to say a bit more than just a tree, any binary tree, but say you want to specify what it means to be a tree that is complete at depth n. So you can take this predicate for trees and just modify it to ensure that it's a complete binary tree of depth n by writing something like this. You match on T, and when it's leaf, you say that n is 0, and when it's in the node, you recurse and you change the value of the depth. You can also do something like this. It's equivalent. You do in your meta theory, you do something that says this tree, this logical tree, is of depth n, and then you say that your predicate for complete trees is in fact just the predicate for trees, and you have some additional pure fact on T. And you can write those like this. It's the same. Going a bit further, if you don't really care about the structure of your tree, but you would be interested in saying it's a search tree, binary search tree, for some set of elements, and you don't really care about the structure of the tree, you could say for a set E, P points to this set through the structure of a search tree if there exists some binary tree such that P points to this mutable tree structure, and search T and E, which relates the tree structure to, like, the logical tree structure to the set E. And so the relation between the tree and the set would be something like this. Leaf contains nothing. And if T1, T2 are search trees for E1 and E2, the set E1 and E2, and X is bigger than all of the things in E1 and smaller than everything in E2, then node X T1, T2 represents the set X E1, E2. And so then you have something that hides as much as you want of the implementation with your binary, with your representation predicate. And so you can have higher level things. So those kind of things would be hard to do maybe with I was about to say that it would be hard to do in some automated prover, but I'm not sure about this, so never mind. Yeah, you can maybe keep the mic.
Thanks. So the predicate for the binary search trees gives you something that's a little bit weaker than separation, right? So you might be able to use some weaker predicate about the heap, because the keys have to be strictly smaller on the left.
Yeah.
That gives you some kind of a separating guarantee that's weaker than separation. See what I mean?
No.
Maybe it's stronger. If you have a binary search tree, you can split the heap into two separate heaps, one from the left and one from the right.
Yeah.
So somehow it implies some.
I mean, if you want to do to prove some algorithm on your tree, then you need to say, okay, what is the tree? And then you'll be able to split the things up.
Yeah, but you don't need to say that it's a binary search tree anymore, because.
Oh yeah, you can hide. Yeah, that's a good point. You can, if you have something like this,
yes,
it can be M search of E, and then there exists some other structure, and then you're fine. You will specify your all of your function on search data structure with some precondition like this, postcondition like this, and this doesn't mention trees. Yeah.
I mean, you don't need the M tree there.
Yeah.
You don't need it because they have to be separate because of the keys being smaller.
I don't, that
I
I
can
don't
take
think
that
so.
offline.
Okay. I think that, I mean, you still need to say it is somewhere stored in the heap.
Stuff. I guess non-dangling. Yeah.
But search TE is just a pure predicate, T is just a pure tree, so if you don't have T points to something, then you're not talking about any heap whatsoever.
I guess you want to say nothing dangles, right? Until you're the leaves. But you see what I mean?
I'm not sure if you can do that. Maybe.
Okay, maybe you should discuss that afterwards.
Maybe, yeah.
Sorry.
Okay. All right. So okay. So there are some structure with sharing. It's a bit more awkward, as you will see. So say you want to represent the union-find data structure, which so you can do it with an array of ints, of integers, but you can also do it with a simple data structure, which is type node. Again, node is equal to node ref, and so you have your just have a bunch of cells with pointers to other cells, and so they point to other cells. So it's a tree but reversed, and the last one points to null or to itself, the same. So it doesn't matter. So this structure implies some equivalent relation, which is the union-find, union-find intended equivalent relation. And so two elements are related if they point to the same root. So if you want to represent this, you have to do something like some iterated separation of all of the nodes, nodes, I guess. So you can formalize this as this when you iterate on a finite map. So it's awkward, but you can do it. And then you need some pure predicates to say what is the root of something. So you have something that represents the structure of the heap inside of your logic, and then you reason about it in the heap in your logic. And then you have a union-find predicate S that does say, oh, there exists a big map that represents somehow the structure of your union-find data structure, and then you proceed. And so then you have is equiv AB that requires as precondition some union-find of S that you don't really mention in your program, but you know that A and B are in this structure, and it returns true if and only if they are related in the equivalent relation. So that's one way to have some sharing. Okay, let's go back to something a bit more precise. So you have we have mentioned separation logic triples. So what do they mean exactly? So you have H, which is your precondition that talks about the heap, T, your program, and lambda X of H prime. H prime is the post condition, talks about the heap, and you have some value that is returned that we say lambda X, and H prime can talk about X. You can have also HTQ, and Q is of type A for some type return type A, arrow heap, arrow prop. So you don't need to have this particular form. Okay, so let's see some examples. So you have a reference. So we've seen this one already. We have nothing like empty heap as a precondition. Then ref of 3 returns some location R such that R points to 3. If we have just 3, you have no allocation on a heap. So it returns some value that is equal to 3. And we store it, I mean, we have it just as a pure fact. It's not in the heap. When you load some reference, you do bang of R, you get the result, and you get also the fact that the R is not lost. And you have when you have a function called like inc R, you can describe the precondition, the postcondition like this. Okay, so if you in general, if you want if you want to specify a function, you do it like this. For every A, which is the argument of the function, sometimes you need I mean, for every A, that is the argument of the function, you might need some B also that relates the thing that are not the arguments, but that's so it's technically not the most general. and then you specify f of a. So it's basically saying your function is specified only when it's called with some argument, and then you say pre and post. So for example, the specification of increment r is r points to n, r points to n plus 1, returning nothing. And that has to be with that has to work for every r and r on n. So, oh yeah. So when you specify the basic operation on memory cells, so you don't really need more than all of those things, those three things to manipulate the heap. Everything else can be, built on top of those ones. So the allocation, the ref of v is, normal, empty, and returns some r points to v. This one we've seen with 3, and for storing, like for r receives some value v, you have the post condition is always r points to v.
Yeah, sorry, I must have blinked and I got confused.
Yeah.
What is the lambda r dot and then expression?
Yeah, it's
And also, what's the difference with like there exists x such
yeah,
that
yeah, good question. So x lambda x h prime x is the name of the value returned by t. Yeah. Maybe I should not just look at OHAD when trying to see if people understand.
But so it's not binding something to a scope.
It is binding everything in h prime.
All
It
right.
is not a program variable.
Right,
It is usually, though, the same, letter.
right. But if you add, for example, if you have more separated terms afterward, they can cx.
Yeah, so in
as
general,
the result of the computation. Sorry, as the result of t.
yes.
Okay.
Yeah. Thanks. So if you had like, so this is this one example. Bang of r returns some x. This x is equal to 3, and separatedly, r points to 3. So this is one example. Wait, never mind. There is no x, but you could write x instead of the 3. That would still be okay, because you know that's equal to 3. And so for storing in a reference cell, the precondition can be a bunch of different things that are all equivalent. So you can either know already what is in the cell. So in this case, it's simple to write it like this, like it was W, it's being overwritten by V. You can so it's and then you know it. You know it because you write the specification for every R, V, and W. But you can also write the W inside existential quantifier in the precondition, so that you can apply it even when you don't know the value. And this is shortcut for just this. Like R points to if there exists some W such that R points to W. Okay. So if you have a function that has some precondition, and so like factorial has some precondition that n is not 0, so it's a partial function, you can have it either here as a pure fact or as a precondition. It's those two things are equivalent, as we'll see later. And okay. Yeah, okay. So how do we specify what this means? So if you have a triple HT lambda x h prime, what does this mean in terms of your operational semantics? So those examples in the slides are mostly total correctness. So that would mean that for every memory that satisfies the precondition, there exists some value and some memory, such that our T in this memory reaches some value, some n value m v, such in some memory m prime, such that m prime satisfies the postcondition, inside which we've replaced the returned x by the returned value. So there exists. So this is assuming a deterministic language. If you have any non-determinism, this is basically useless. So you'll have to do either for every state that is reached, it satisfies the postcondition, or if you want something, so if you do this, then you lose the total correctness. You don't know that it's terminating. So you can combine both with the WRP that I've talked about yesterday. But you can replace this with what you know. The point is more about the H and the separation. So the first line is important. So that's assuming that the triples describe the entire state. So that means that this can be run only, the precondition needs to talk about the whole memory. So that might not be practical. So we'll see this after. It's a 1/3. Oh yeah, and see if you have a more generally, if you have a Q instead of just this form, it's the same. You apply Q to V to talk about the return value. But what is more interesting, because we're talking about separation logics, is that you can talk about a triple that talks about some part of the heap only, which say that it's M1. The rest of the heap would be, say, M2. And we have to say the triple, when we talk about just M1, we have to say that M2 is unchanged. So the triple HTQ becomes something like this. For every M1, M2, if H talks about M1 and M1 is disjoint from M2, then we can reach a value in a new memory M1 prime that satisfies Q. And in fact, the rest of the memory is still there, and it's unchanged. So M2 is unchanged from this to this. So in fact, this can be reformulated. Wait, never mind. There is also one more thing is, let's say you have some language with garbage collection. What happens if you want to throw some things away? So let's say you have a very weird program, myref of x, which builds a reference to x in the following way. Let R is equal to ref of x, so it builds it allocates something that points to x, and then S points to R in a new reference cell. So we could specify it like this. My ref of x returns some pointer R that points to x, and there exists some S that points to R. So we would like to be able to throw this away because we cannot do this. So if you are in C, that's a memory leak, so you don't want to do this. But if you are in a camel, that's fine. And so you want to throw this away. So we need the postcondition to describe only a subset of the resulting heap. So that becomes something like this with a bit of a mouthful, but that's fine. So basically what was added was this M3 here. That is disjoint from the memory entirely, could have been allocated, could even have been from M1 and thrown away. It could not have been from M2 though. And so the postcondition is always talking about M1 prime, and the M3 is just talking about is disjoint from the two. So this disjoint is of course supposed to be transitive. M1 is also supposed to be disjoint from M3, even if that's weird, like this.
It's step of M1.
Yeah, it's yeah, that's a bit. It's not nice. So we can repackage things a little bit. So we'll introduce a new heap predicate that is just GC, called like a garbage collection. And GC is defined as there exists H, a heap predicate such that H. And so that satisfies every heap, because H could be just the heap is the heap. Like it could be lambda M true. And so our separation logic triple can become a bit more concise, like this. HTQ if for every H prime and M, so H prime is the framed part. If M satisfies H star H prime, then there exists a value blah blah blah, such that Q of V star H prime unchanged and some GC. And this is talking about M prime. All right. Summary. It was I went fast, so it's okay. Okay, so now we'll talk about the frame rule, which is the important bit, basically. So say you have
just, yeah. Talking about cleaning up the types, I'm wondering, this looks a bit like a key function space, like the fact that you're saying for any extension H prime, I have a function from like
yeah.
the extension to that extension. So I wonder whether we could like express it in like a
Yes.
Yeah, I don't have anything smart to say about this, but probably. Yeah, I'm sure there are smart things to say, but I don't know. So okay, so say you have specified your function, you work very, very hard to specify the function inc that takes some R2, R points to 2 and produces R points to 3. So we would also be able to prove the following, like it doesn't talk about S. So we'd like to say that if we have S that points to 7, then S points to 7 at the end. So can we deduce this from this to this? Well, yeah, we can even have more generality for every H, and that is called the frame rule, and it looks like this. So you have if you have a triple that talks about T, H1, H1 prime as postcondition, you can just extend it with H2. So H2 here, H2 here. So that seems reasonable. That's the point of separation. So it allows local reasoning, as I said earlier, and the composition of specifications. One good thing to say is that is incompatible with the traditional hologic way of writing rules. So for example, and actually just mostly for assignments, the rule in hologic is this. P holds after an assignment if P in which the assignment was made in the logic, if it's true before, if it's in the precondition. So because this X is both a logical variable and a program variable, every time you need to extend your state, your precondition with something, if you want to have it in the postcondition, you have to say something like the T does not modify any variable that is next to it. So it is typically awkward to have this, and separation logic doesn't have like that cannot modify things in the logic. So the program cannot modify things in the logic. The logic talks about the state, which is basically the heap. In practice, you have also things that are not in the heap that are in the program. So like local variables. And then for that, you need to reason about it in other ways. So either substitutions or environments or some local state. Yes.
Are there any side conditions for the
Here?
form you wrote there?
For this one?
Yeah.
No.
No side conditions.
Yeah,
So
that's
X can occur in H2. And the free variable
No.
H2 and
Oh, yeah,
the
yeah.
ones can overlap.
yeah, so no, but you would have a hard time. I mean, it depends of your of how you write things. But if you have X that is in H2, that would mean like you have a free variable in the precondition. I guess that's weird. But there is somewhere the definition of this specifically. Where is it? Never mind. I don't know. So yeah, no. It's X cannot occur in H2. That's that would be bad. That would be bad if that's allowed somehow, and you have a free variable in H2. You should exclude that.
But I mean, we've been having free variables all over in the program fragments, though, right?
The fragments. So
like your rules for state. I mean, there was like, like R for the reference as a free variable.
yeah. So every time it's in your metalogic. So it's yeah, you're right. So when you compose those two things, actually what it says is, so this rule, it would be Like you have a Q here, and when you compose it with some H2, the lambda x, the x only goes to the left hand side. So the more general rule that talks about QQ here, I don't know where it is, but it propagates the x only to the left. So actually doesn't, this rule doesn't exist like in formalization. Typically, you just talk about how you compose the postconditions, and the postcondition talks about the value, and if it's, and the frame rule doesn't talk about the value for the external thing, because it doesn't make sense. All right, I think I would be, yeah, so one last thing that is interesting. So say that you have a ref of 3, you know that it returns some R that points to 3. But by the frame rule, we know that we must have this as well. So S points to 5, ref of 3, and then R points to 3, star, S points to 5. So this means that we know that this ensures that R and S as distinct. So ref of 3 can allocate, will allocate some reference, but we know that this S will be different. So this means that this R really depends on, this statement is true, but this R does depend on the initial memory. So if you try to make it weird, I try to know this R and put it in the precondition, then the allocation would just, when it's instantiated, it would just choose another R. All right, and then I think that's it for today. Thank you. Yeah, Sam.
Oh, that's Mike. Oh, two mics. This one is on, I think. So you showed these examples with references.
Yep.
Does anything go wrong if we try and do higher order state?
I
know it's been mechanized in Iris, but
so you can store
functions which
Functions.
themselves may
mention the heap, that's fine.
mention the heap, or that you may store in the heap.
Yeah,
That's-
the function you can store in the heap.
You can store a function in the heap that
Yeah.
can itself manipulate the heap.
So it is a good point. So if you do it like in the formalization of heap lang, this is substitution based. So you don't have any free variable. You don't have a closure. So there is no problem there. It's just a value, one of those values. If you are a bit more serious about your programming language, then you need to have some notion of closure, and you need to have this representation as as what happens on a real machine. When you store a function, you store the environment that goes with it in actual in the actual value. So this is what happens in what we're doing now in Hoare Camel.
Okay, and it doesn't cause any problems.
No, I mean, this is mostly untyped. What happens? It kind of is okay because we're proving the things are okay. But what is interesting is to try to use the types in order to have an easier, life when we're actually proving programs. So we do have some helps. Like every time we're returning a value, we want to say, oh yeah, never mind, this will be only of this form, so that whenever you apply this lemma, you don't have to worry about if the value is indeed just a Boolean or if it could be something else. So when you apply the lemma, you are using the types to help you have some hypothesis about the value that was returned by some function.
Let's thank John.
Thank you.